Okay, so for this, it should be the same. Okay, we have linked the system like this, system of the body like this, and we would like to find the velocity of distance B and angular velocity of log AB at the instant. Okay, so we define the motion for each part like this. Plank OA is the rotation about a fixed axis. Okay, link AB is the general plane motion, and piston B is the rectilinear translation. Okay, according to this, we do the same thing for the first step. We know that link OA is the rotation about a fixed axis, and we know omega OA from the problem. So then it's maybe better to starting with the link OA first. And from the link OA, we may draw the picture and imagine that according to the omega, that is a go positive side dimension with counterclockwise direction. Okay, so then is we may predict that velocity of point A should be to the left. Okay, and it is confirmed by the cross product here. That is we already know omega OA is 12k. Okay, because the problem gives us that counterclockwise and is consistent with the positive k direction. And also for ROA, we set up point O as a reference. Okay, so ROA has just only one component, that is 0.8j now. And after that, we cross product here, we get the velocity vector of point A equal to minus 9.6i. Okay, the negative sign show us that is moved to the left. Okay, it's confirm the sense that this is moved to the left. And after that, we do the same step. That is for finding the velocity at point B now. Okay, now we know velocity at point A vector, the vector of velocity at point A, and we would like to find the velocity of point B. Okay, we set up point A at the reference point. So then we set up the axis to point A. Okay, and then we form the equation that velocity of point B equal to velocity of point A plus omega AB cross product with RB sub A. Okay, according to this, we already know velocity of point A now, and omega AB is the unknown that we would like to solve. But position vector of point B with respect to A, we can find from the picture that we set up the axis at point A. Okay, so then we can solve for this equation, and we found out we have two unknown, that is VB and omega AB. Okay, two unknown with two components in I and in J components. We decompose it for the scalar equation. For I components, we have the first equation that we can solve for omega AB, that is equal to 12 radian per second. And for J components, after we have omega AB, we can determine for VB, that is equal to 7.2 meter per second. Okay, that is complete this problem. Okay, so for the second one, okay, we have done it already for the group activity, right? And we may solve this problem again together. Okay, so for the case that if we apply in the technique of instantaneous point of zero velocity, okay, we find the IC. Okay, we draw the line perpendicular to VB and VD. Okay, and we can find the point of IC as shown in the picture. Okay, and we set up the reference at point IC. Okay, and for this case, we can determine RB sub IC from the geometry. Okay, and we found that RB sub IC, the magnitude of RB sub IC becomes 0.4, and for the magnitudes of RD sub IC become 0.56. Okay, so according to this, we know that VD is equal to 3. Okay, that is given from the problem. Okay, and VD for when we apply the IC technique, we found that VD is equal to omega BD times RD sub IC. Okay, so then we can determine for omega BD equal to 5.3 radian per second. And you will see that actually we solve by scalar equation. So then actually we obtain just only the magnitude of omega BD here from calculation. We determine like this. But for the direction, we have to consider the motion. Okay, the motion is tend to moving rotate in counterclockwise direction. Okay, according to when D is moving to the right. Okay, omega BD should be rotate in counterclockwise direction. Okay, and for BB, okay, where is the of point B? What's that? When we found that omega BD is equal to 5.3, okay, we cross product with B sub IC, but now it is a scalar equation that is equal to time omega BD is when we multiply with the arm RB sub IC that is equal to 0.4, it's become 2.12 meter per second. Okay, and if we consider link AB, okay, link AB VB is equal to omega AB RB sub AC. But now we already know VB from link BC or from link BD now. Okay, so then we substitute, and then after that we can find omega AB that is equal to 5.3033 radian per second. You see that it is for this analysis, you will see that we obtain just only the magnitude. The direction actually we don't have. Okay, if we would like to have, if we would like to know the direction also, okay, we have to predict by ourselves. That is for this case, when D is moved to the right, BD should be rotated counterclockwise, but AB will rotate in clockwise direction. Okay, as shown in this picture, as shown in this. Okay, and if we move to next, that is the case that we apply the absolute motion analysis instead. Okay, for this case, I set up the axis at point A. Okay, and you see that for this slide, I saw a little bit different from when we working together on Wednesday. We may set up the angle in different theme, in different direction like me. Okay, but for this example, okay, I set up the axis. I set up the angle that it should be rotate in direction, in same direction. As is may show you that this is the you will see that it will show you the direction also. According to this, if we set up the theta AB measure from X, okay, measure from X, that is it means that it's counterclockwise as the positive one. Okay, and for BD, okay, instead of X, we measure the angle from Y direction instead. Okay, so then it is counterclockwise also. So according to this, so then we define theta BD here, we define theta AB here. Okay. Okay, so for the absolute motion analysis, we may set up the angle. It depends on us. If we define like this, so then you see that it's measured from the reference line to the point, to the arm that is has the motion. Okay, and for this case also we measure from the reference line that is X to the line of motion. Okay, we will not set up the coordinate like this. For this case, we will not set up for theta AB is clockwise. This is not correct, okay? Because normally when we measure the rotation, we have to measure from the fixed or the reference axis. That is for this case, theta AB is measured from X. So then counterclockwise is a positive. Okay, we will not measure from the lines of that has motion back to the reference. This is not correct. This is not correct. And the student is always confused to that. Same as this, okay? If we set up X to be the reference, so then for this case, theta BD, if we set up this side, okay, it should be clockwise as a positive, okay? But for this case, I would like to reduce the student confusion, okay? So then I try to set up the same direction, okay? Same direction as theta AB. So then I set up the reference in different one. So for omega, for BD member, I set up Y as a reference instead. And so for this case, measure from Y that is reference to link BD. That is the link that has motion. Okay, we found out counterclockwise as a positive also. And for this case, we have to determine the position of point D in terms of the angle that we already defined. Okay, and we found out XD is become this term. And so according to this, we take the derivative to the position XD. We get this term, okay? Substitute we change theta AB dot and theta BD dot to be omega AB and omega BD respectively. And then after that, we keep it like this, okay? And we consider YB, okay? So for YB is equal to 0.4 sine theta AB, and also is equal to 0.4 cosine theta BD. We take the first derivative to YB, okay? Let's we get VBY, okay? That's you will see that for this case we have sine, okay? That is for the case that we use theta AB, we have this term that is 0.4 cosine theta AB omega AB. And if we use BD instead, we have 0.4 minus sine theta BD omega BD. But we know that theta AB and theta BD are same, that is equivalent, which is equal to 45 degrees. So then sine cosine cancel out. This is equivalent. Okay, so then we have the conclusion that omega AB and omega BD, the magnitudes of these angular velocity are equivalent. Okay, but the direction is not. Okay, omega AB is counterclockwise as we assume, but omega BD it is clockwise. Okay, it is clockwise instead because we set up counterclockwise as a positive. Okay, we do the same thing. We back substitution to the equation A. Okay, and for that, okay, we substitute omega AB to be minus omega BD here. And after we solve this equation, we obtain omega BD equal to 5.3. Okay, and also omega AB is become minus 5.3. So that means that omega AB is opposite to the positive sine function that we set up at first. Okay, so it's moving. We set up counterclockwise as a positive. But if you imagine that omega AB should be clockwise instead. Okay. And for relative motion analysis, okay, you see that for this case, it should be the same. Okay, same step. That's for the previous problem. Okay, we starting with point A. That's this is just only the rotation about a fixed axis, right? And we know that RB sub A is become here. Okay, and VB is because it's rotation about fixed axis, this is equal to omega AB vector cross product with RB sub A now. Okay, and omega AB is we write in vector form, is become omega AB K here. And after we cross product, we have this equation. And now we cannot find omega AB. We leave it first. Okay, and move to next. Okay, that is if we consider link BD. Okay, and now we know from the problem that VD, we already know the velocity. Okay, so then we may set up point D as a reference instead. Okay, so for this case, we may set point D as a reference, and we can find VB with respect to VD instead. Okay, and from the velocity, okay, equation, we have VB equal to VD plus omega BD cross product with RB sub D. Okay, but RB sub D, we set up D as a reference. Okay, so RB sub D become this vector. Okay, after we substitute into this equation, we obtain equation 2 here. And we have to solve for equation 1 and equation 2 for two unknown. That is omega AB and omega BD now. And after we solve, we obtain that omega AB and omega BD should be same magnitude, but it's different direction. Okay, so after that, we solve for the equation, two equation, and we obtain omega BD and omega AB. That is to be this. Okay, omega BD is become 5.3 positive. This means that is counterclockwise. But omega AB is become negative 5.3. It's just the opposite sides, mean that it should be clockwise instead. Okay, let's complete this problem. Okay, then we move to next. That is we have a disc having a radius of 0.75. Is rotated with an initial angular velocity of 2 radians per second and has the constant angular acceleration of 1 radian per second squared. We would like to determine the magnitude of velocity and acceleration of point P. Okay. Okay, so for this is the problem of rotation about a fixed axis. Okay, we already know that the wheel has the rotation about the fixed point with the initial angular velocity, that is omega 0 equal to 2 radians per second, and is moving with a constant angular acceleration, is alpha equal to 1 radian per second squared. So for this case, we can find omega at any time t. That is now we would like to find omega at t equal to 2 seconds. For that, omega is become 4 radians per second. And from the omega that we already know, we know angular velocity already. We can find the velocity at point P by omega times r. That's become 3 foot per second. That is the first question. Okay, this is the first answer for the first question. And then we move to the acceleration that is composed of two components. For the rotation about fixed axis, we have two components, same as the circular motion. Okay, AT is equal to alpha r, that is equal to 0.75 foot per second squared now, and an is equal to omega square r, that is 12. Okay, so the magnitudes of acceleration is become 12.0231 foot per second squared here. This is complete this problem. And for the last one, we have the circular cam is rotating about a fixed point O with omega equal to 5 radian per second, alpha equal to 1.5 radian per second squared. Okay, with the dimensions as shown, okay, we would like to find velocity and acceleration of the plate when theta equal to 30 degrees. Okay, so now we set up the reference at point O. Okay, and we measure the plate C, and this is we define the x as the position of the plate. Okay, so according to this, we can find out x is equal to 120 sine theta plus 150. Okay, we can find velocity of point C, that is velocity of plate, is equal to first derivative of x with respect to time, and AC is a second derivative of x with respect to time. Okay, and after we take the first and second derivative we obtain here, and then we substitute each value from the problem into the formula that we already derived. We obtain velocity of point C and acceleration of point C here. That is let's complete this problem. Okay. For this, I think it's maybe next time. That's this is about the we will apply the kinetic. This is this problem is about the kinetic problem of the rigid body. Okay, we may talking about this topic next for next video.